Well, good afternoon, everyone. Hope everybody's doing well on their end. We are live from the American Chemical Society headquarters in Washington, D.C. And as our viewers continue to join us for today's webinar, let me briefly set the stage for today's session. My name is Jeff Standish, and I'm the Community Manager for our Separation Science topic area in Sci-Mind. And let me formally welcome you all to today's Sci-Mind Separation Science webinar by Dr. Nicholas Snow, titled Developing Chromatographic Methods, Where to Start. This webinar is being brought to you by the American Chemical Society's Department of Professional Education and our newest training product, Sci-Mind. We are thrilled to have Nick Snow from Seton Hall University returning to our webinar lineup. Nick and I have done a couple webinars, and given Nick's affinity for sports analogies, the Sci-Mind team is excited to have him batting leadoff for our active cohort session in separation science. Just a few housekeeping items here in a second, but first let me take a few seconds to acknowledge and thank our many subject matter experts in the Sci-Mind program and some of our content contributors, Chromedia.org and Agilent. The Sci-Mind team would also like to thank Waters Corporation for their continued sponsorship of the Separation Science topic area. So housekeeping logistics. For those of you that are new to the Sci-Mind webinar format, it's a bit different. So that we can enhance your viewing engagement, Nick will be providing two 20-minute discussions, each of which will be followed by a 10-minute question and answer period. For optimal viewing, we suggest that you minimize all other applications, except for the GoToWebinar viewer and the control panel. All attendees are muted and will remain muted during the public webinar, so please utilize the question window in your control panel to submit your questions. You see it pictured there on the screen. You may submit your questions at any time, and Nick will be glad to answer them as they come in. Additionally, we ask that you, the audience members, weigh in on a couple of poll questions that we'll be asking throughout the next 60 minutes. This information will be helpful both to our speaker and the Sci-Mind program, so in advance we appreciate your participation. So why don't we get started with the first poll question. You should now be able to see the first poll question, and I'll leave it open for about 30, 40 seconds, so if you could answer at this point. Got about 10 seconds left, so get your answers in, please. All right, I'm closing the poll. Thank you for your responses. We'll look at those responses in a little bit later on in the webinar. So at this point, I'd like to introduce Dr. Nick Snow. I'm pleased to introduce Nick. He's one of our Sci-Mind experts and an accomplished researcher from Seton Hall University. Nick received his PhD from Virginia Polytechnic University and was a member of Dr. Harold McNair's lab. Dr. Snow became an assistant professor at Seton Hall in 1994 and then gained full professorship in 2003. Nick wears a couple of hats currently. He is the director of the Center for Academic and Industry Partnership. He's active in teaching, and he recently became the chair of the Chemistry and Biochemistry Department at Seton Hall. Nick's research and that of his lab group are highly cited, and it spans a range of industry sectors. His group focuses much of their effort on basic applications for gas and liquid chromatography, as well as assorted hyphenated techniques. Nick has been a subject matter expert within Sci-Mind since it launched in 2012, and we greatly appreciate his continued contributions to our training community. Before I hand it over to Nick, given that it's early October and the baseball playoffs have just started, I know Nick will appreciate me saying, let's play ball. Nick, the screen's all yours.
Jeff, thank you very much, and very glad to be here playing ball from sunny South Orange, New Jersey, and welcome to all of you all over the country and all over the world, and a special welcome to our Sci-Mind separation science cohort members. I'm glad to be, very glad to be interacting with you again in the Sci-Mind program. It's a lot of fun to interact directly and to do it over the internet from the comfort of our offices and homes. So we'd like to talk about chromatographic method development today, and of course I think, as most of you know, that's a topic that we could do weeks and month-long and sometimes career-long learning about how to develop methods. I know after 25 years I'm still learning new things about method development, and certainly every time I talk with a colleague about method development in chromatography I learn something. So we've got a lot of work to do, but we'll get started today a little bit. Think a little bit today about all the kinds of questions that we want to ask before going into the lab. I think that's one of our challenges, just asking enough and asking the right questions before we start going and injecting things on our instruments. One of the challenges that's always a fun argument, if you really want to get our subject matter experts going, ask them a question about a separation science problem you have and ask them whether they'd use GC or HPLC for that problem. I can promise you a spirited discussion if you have more than one of our subject matter experts in the room with you in Sci-Mind. And then the other thing we'll talk about is what kind of data do we get to start with when we figured out what we want to do, how do we get started. We're going to try to do that with really some application examples and think about some examples from the work we've done here in my lab here at Seton Hall that are really related to general method development goals. So that's kind of where we're going to go, and we'll do this again in 2 20-minute segments. Feel free to shoot questions in through the question window. I will do my best to answer them as we go, or that will be a great opportunity to start off our question sessions. But let's think a little bit about method development now, and I think one of the challenges that we start off with is even thinking about what is the problem, what are we trying to solve. What are the goals of our analysis? What do we need to get done? Are we going to be running this method 100 times, 1,000 times, or maybe it's just a one-off? I think that really impacts our development process and impacts the kinds of resources and the types of instrumentation that we're going to use and those sorts of things. We're certainly going to think, along with our chromatography, about sample preparation. I don't think we do any chromatography today without some amount of sample prep, and that also has an impact of what we're going to do instrumentally. Thinking about columns, how do we choose a separation technique? And then finally, I do have a few comments about data analysis. I've seen in the discussion among our Sci-Mind cohort this week that quite a number of you are interested in talking about different calibration techniques and that sort of thing. So I put some introduction to that and a few comments to that in toward the end. So that's where we're going to head, again broken up into two segments. Let's think about the problem we're trying to solve, and these are just a few of the questions that to get us started, and that's really what these next few slides are going to be about, is thinking about all the stuff that I want to think about ahead of time before even going into the lab to try to run or develop my method. First of all, I like to know, of course, what we're looking for. What kind of matrix is it in? Is it simple? Is it something as simple as an active pharmaceutical ingredient in an aqueous solution? Well, that sounds simple, and maybe it is. Or is it something really complex, like that same active pharmaceutical ingredient that's excreted in somebody's urine? That's going to impact our method development. Certainly, we're going to identify the resources we have. Often that GC versus HPLC question comes down to which one we have in the lab, which one has the available time on it, and who can run it. Some other questions that we'll look to answer is think about our customer a little bit. Who's going to run this method? In my lab, I think about, I've got PhD students in my lab. They can do just about anything. But maybe we're developing a method or working on something or consulting with something that's for people that are going to run that have associate's degrees or even high school degrees. We want to think a little different a method for them versus a method for my PhD candidates. How many times is it going to be run? Is it, again, 10 times, 100 times, 1,000 times? That impacts the type of development we're going to do. what kind of samples, how we're going to get them, and of course, at the end of the day, one thing I've learned in doing some academic management, we're always thinking about what the budget is. So those are all questions that we want to think about. So talk about a few fundamental goals, and you probably in other short courses you may have seen something like this. Here's a triangle. And in terms of analytical method development, and this isn't just for chromatography method development, I can really think about that in terms of some major goals. We've got speed. One thing we love to do in industry is run our methods fast. Fast, fast, fast. Get the samples through. How many samples can you run in a day? Another goal we have in chromatography, of course, is high resolution. How many peaks can I separate? I'm going to need to get them really well separated. I need to get all kinds of matrix components out of there. So we want high resolution, we want fast, and of course we like methods that are easy to run and reproducible, high sample capacity, easy to inject on, and those sorts of things. Well, I like to think about those, and this is not a new way of thinking, but it is a useful one, I think, as the three corners of a triangle. And what I'm going to tell you as somebody who's been doing this for 25 years is that pretty readily I can give you two of those. So think about this, and we'll think about this with some chromatograms a little later in the session. Okay, if let's say I want a fast method. Well, if I want that method to be fast and easy, look at that left side of the triangle. That's as far away from resolution as you get. So what does that tell you? If it's fast, if it's easy to run, has high sample capacity, or is inexpensive, it's probably low resolution. I mean, I can do things fast and easy, but I'm going to sacrifice resolution for that. Let's say I want something that's fast and high resolution. We can do that. I'm going to show you some examples of that a little bit later, but that means it's probably not going to be the easiest method in the world to run, or it's going to have very expensive instrumentation, or it's going to have some combination of the two of those problems. Finally, let's say I want something that's high resolution and something that's easy to run. Well, we can do that too, but it's probably going to be slow. That means maybe I'm just going to use a really, really long column in my standard instrument to generate the resolution. What we're going to find in our method development exercises is that what we really end up doing or starting with in industry is some compromise between those goals. And most of the time I will tell people when I'm consulting with them all the time, I tell them, okay, we talk about these goals, I can give you two of them and I can do that pretty easily. But if you want all three, that's an extremely difficult problem and is going to involve compromising some of them. So that's a little bit of a of a goal to start with. Let's think about some scientific goals and what do we want out of chromatographic methods. Things that we're looking for, we're going to talk about, and we'll talk about in some more detail in a moment, but here's a couple of key words: selectivity and resolution. Selectivity is a measure, if you go back to organic chemistry in college, you learned about selectivity. Maybe you learned about a reaction that has two possible products. Adjusting that reaction to get your product of choice is an example of selectivity. In chromatography, we think about selectivity as the chemistry in our column, or the type of detector that we have that helps us detect one compound instead of another compound in the matrix. Do we get a good separation, or do we use a detector for that? Resolution, of course, in chromatography, that's kind of the ultimate goal of the method. We want to get the resolution that we need. The peaks are all separated from each other. When we think about these together, selectivity is a measure of the chemistry that we bring to bear. Resolution is really going to be bringing all of our tools to bear to achieve a separation. A couple of quick definitions. Let's see how those may be applied. So let's get to some chromatography. Well, it's not quite time to get to some chromatography yet. Let's think about getting to know our samples a little bit. This is just a short list of physical and chemical properties that are the kind of things that when I was asked to do this webinar, I started thinking about this again. What are the kinds of things that I like to know about my analytes and about the sample matrix before I even go into the lab and start working with it? What are the physical properties? I start off with what's the chemical structure? What is it that we're looking for? Do we have data on this thing? Melting points, boiling points, vapor pressures. That's going to help us decide, can we do gas chromatography on this, or are we doing HPLC? I'll share with you a little bit of a secret. I'm a bit more of a gas chromatographer than an HPLC, than a liquid chromatographer, so I tend to go to gas chromatography first, and that's just really out of my training. So you're going to hear me say things like, can I do GC on it, or am I stuck with HPLC? That's just a little bit of my background. Some of the other subject matter experts can argue with me on that. I'd like to know solubility of the analytes. I'd like to know what's it soluble in. That's certainly going to help me in sample preparation, or if I have to do HPLC, I certainly need to know that it's soluble in the mobile phase. I want to think about spectral data. What is the what's the absorbance? What's the spectroscopy of this? Do we have spectral data? Do I have a mass spectrum? Do I have a UV spectrum? Is there an NMR out there somewhere that can help me? Think about the pKa. Is it ionizable? That's going to impact, again, sample prep or HPLC. So lots of questions that we can ask about the compound and about the matrix. Other things I like to know, of course, are their chemical properties. How reactive is this thing? Is it thermally labile? That could be a problem in gas chromatography if the thing's going to decompose on me in the inlet. Is this something that might react with my mobile phase or with components that we typically use in the HPLC? Again, those are the kinds of things I want to know as much as possible about my analytes and the sample matrix before we even go to the lab. This helps us make decisions, and one other thing that helps us make decisions is I go to the literature. And of course, this is one way to find out all of that other information. Some of the things that we didn't have back in the day is, today you have Google Scholar even, and one of the things that I've very commonly done is typed in the name of my favorite compound into Google and see what comes up, or Bing, or whatever your favorite search engine is, and see what shows up there. You may be pleasantly surprised at what you find. You probably get linked straight to the manufacturer and all that information. You might even get the MSDS out of it or something like that. We go into SciFinder, which of course is ACS's chemical abstracts search engine. Again, it's not too tough to go into SciFinder and type in the name of your compound and gas chromatography, or the name of your compound and liquid chromatography as keywords, and see if there's something out there in the academic and the peer-reviewed literature on it. Certainly check your databases. Certainly if you have a database of standard methods or some of the other databases that are out there, like Scopus or Science Direct, or one of those that might be available at your library, check those for your compound and work in chromatography on it. You may find something. You may find an article that gives you a good start on the method. And then finally, of course, one of my favorite things to do, especially for compounds that are already out there on the market, check your favorite column and instrument vendors and go to their application notes database, which you can usually get online. Just go in there, type in the name, see what you get. Again, you'll probably get a lot of hints and a lot of help in terms of how to get started. In fact, you may find a method already out there that you can much more easily adapt to your work than starting from scratch. So those are a few comments. And let's think about one other thing before we get into some chromatography and some definitions. What about GC and HPLC? That's always the fun question. And when we think about that, I think about GC first because I started in gas chromatography. But when you think about it, there's sort of some fundamental requirements if you want to run the compound on a GC versus if you want to run it on an HPLC. In GC, you want to think about whether the analyte can be moved into the vapor phase. It's interesting, in previous short courses, actually, in all of Professor McNair's former HPLC or GC short courses, they talked about you need compounds that are volatile. Think about this for a moment, a little homework for you while you're thinking about there. Ask yourself, if I asked you what a volatile compound is, or name a volatile compound, how would you reply? I'll bet a lot of folks right now are thinking about ethanol, acetone, hexane. What if I suggested that for GC, say, caffeine were volatile, or 17-beta-estradiol, or cocaine, to name a few analytes that we worked on in drug testing? Those are volatile as far as gas chromatography is concerned. You can get those through a GC column, but they're not compounds that you think about as volatile. You may find in gas chromatography that there are compounds that you can vaporize that you don't really think you can. In HPLC, the main requirement is that the analyte's soluble. And that's, just need to have it soluble in the mobile phase, and you can probably get it through a column. A little bit of a fudge on the slides here. Dirty samples in GC require cleanup. In HPLC, they may require cleanup. You're probably a lot closer in HPLC to a simpler dilute and shoot method versus a more detailed sample preparation technique that we have in gas chromatography. Excuse me. In GC, we'll think about detection. In GC, one of the things we had to do is learn all kinds of new detectors that you never heard about in undergraduate school. Things like flame ionization detectors and thermal conductivity detectors. Unless you did chromatography as an undergraduate, you didn't learn about those. In HPLC, we get more familiar detectors. We get things like fluorescence spectrometry, UV vis spectrometry, things that we're kind of a little bit more familiar with, that certainly have selectivity we can use, so we get some advantage there. Probably what we get in GC more routinely and easily and less expensively is a high resolution separation. And that's another one of those things also that we think about. We can get a lot of efficiency out of a very simple GC system, and in some ways a simpler GC system than the similar HPLC system. So there are a few questions that help us with that challenge. I think the HPLC folks among our subject matter experts would certainly argue that you can do anything by HPLC. My colleague here at Seton Hall, Yuri Kezakevich, who's a great HPLC theoretician, would certainly argue with me on that. The question will be is, can you really do it practically? And a lot of small molecules that are much better done practically by a GC are just better done practically by GC. Those are some things to think about. So how do we generate this selectivity? And really when we're generating selectivity, this is what we're thinking about. How do we bring all of these ideas of chemistry together that we've learned about our analyte, that we have available in our chromatographic system? How do we bring those together to generate selectivity? We can think about it in several ways, and I'm going to just come to some simple chromatographic definitions, but our sampling, sample prep, injection, all of these portions of our analysis can help us to generate that selectivity. First of all, in the column, what is selectivity? Here's a definition from our, probably from our basic notes, from the textbook definition in chromatography of what selectivity is. You can calculate it. It's just the ratio of adjusted retention times. It's also the ratio of retention factors. And if you took it one step further, it would be the ratio of partition coefficients in chromatography between your two analytes. So you've got analyte A and analyte B, the ratio of those partition coefficients generates this number called the selectivity. Obviously, what we'd like to have is use our chemistry to make that selectivity as large as we can practically. Another quick definition, a couple of definitions, and we'll talk about how we use this in method development, is resolution. Here's how we might calculate it. You take two peaks, you take the difference in the retention time, divide by the average of the peak widths, and you get a magic number for resolution. Let's see, it says. And you get a magic number for resolution. So what you can do here, again, this is how a standard way to calculate it, and if this number comes out bigger than the magic number of 1.5, you can, you can declare that your peaks are separated. Here's a question. I've got a question from one of our, from one of our audience that I'll go ahead and answer. Dr. Snow, of course, I've been talking a little bit about GC versus HPLC, and I've been asked if I'm familiar with ultra-high pressure liquid chromatography, and the answer to that question is yes. I will admit that I haven't run it very much, but I will also, state that, ultra, UHPLC, that's one of those things, we can talk about that a little bit later. That's one of those things that probably moves a little bit further away from the ease of use portion of the triangle, even though, of course, we can get very high resolution out of it, we can get speed out of it, but it's also more expensive and more difficult to use than traditional HPLC. So that's where I might place UHPLC on the triangle, is a little bit more toward the speed and resolution corner, a little bit further away from the capacity and ease of use corner. So we think about our goals with that. But yes, of course, we're, UHPLC is a very interesting technique, certainly one worth exploring for the folks that do a lot of HPLC. Let's think about the master resolution equation for a moment. And this is an equation. Do not ever use this equation to actually calculate a resolution, at least we don't. But what you can use this for is to help us think about all of the factors that contribute to resolution. Probably the main one is the number of, you've got three of them here. You've got the number of theoretical plates, our column efficiency. Okay, we've got alpha, the selectivity there in the middle, so there's your chemistry. So you've got column efficiency, you've got the efficiency of the engineering of your instrument. You've got chemistry there with alpha in the middle, so our column chemistry. And then finally, K, the retention factor, is just how long you're in there, because you need to be in the column long enough that you can make a separation happen, but not so long that you're wasting your time. And really all three of these factors come together to help us get resolution. Here's just a few examples to get us started of some peaks at different resolutions. Here's what we might see. Here's some peaks that aren't fully resolved on the left there. You can see a resolution of about 0.7 if it were calculated. Resolution of 1.5 says we have them just separated. One of the things that I try to shoot for in method development is I like my two closest peaks to have a resolution of 2. That way I've got a little bit of baseline in between them, so that when things start to go wrong down the road, I've got a little bit of room to play before the peaks start running together and being more difficult to quantitate. But this gives us an idea a little bit of what we shoot for. And one thing we shoot for in method development is to try to get that critical pair, those two closest peaks, to have a resolution at least 1.5 and ideally about 2. Now I've seen a lot of chromatograms where the two closest peaks have a resolution of like 5. What's the problem with that? Well, you have so much baseline in between that you're actually kind of wasting time. Oh, we've got a discussion on HPLC and UPLC coming up. It says here UHPLC and HPLC only differ by capital cause because ease of use is equivalent. Columns from UHPLC can be employed on HPLC systems with proper consideration of methodology, and I'm not going to argue with any of those points at this point. So I agree with all of that. Thank you for the discussion. So let's move on a little bit. Here we go. Here's also just a little bit again of some basics. Here's the number of theoretical plates and how these things all interact with each other. Just a quick view of the effect of N alpha on resolution. So here's we got a chromatogram. It's not fully separated. We'd like to separate it better. One thing we can do is make our instrument better. We can go to a more highly efficient separation. Perhaps we switch from HPLC to UHPLC and keep as many of our other variables the same as we can. We might get peaks that look like the two in the middle. Much sharper peaks, much faster peaks, and with more separation. That's essentially improving our engineering, but not changing our chemistry so much. Another possibility is we can go back and we can think about changing our chemistry. And you see that in the bottom chromatogram. We've changed the selectivity, we've changed the chemistry, but kept the engineering pretty much the same. So the peaks are about the same width, but they're just spread further apart. These are also some approaches that we can do in method development. So I just wanted to mention a few things about extraction, and it looks like it's getting to be time to to head into our first break. One of the places where we do get selectivity is from extraction. And that's again one of the places where we're going to see some of that. Just wanted to make a few quick comments. Here's a quick plot of looking at extraction efficiency and how many times. You probably remember this back from sophomore organic chemistry. If you extract the sample twice or 3 times and then combine the aliquots, you get a better extraction than if you do it once. And that's kind of what's being shown here. What's kind of interesting is we generate selectivity from extraction based on the partition coefficients, and that's really what we're seeing here. On the right side, we have a legend showing different partition coefficients. You can see that if I just do a single extraction, if I have a partition coefficient of 10,000, you pretty much extract everything. But if I have a partition coefficient of 1, we extract about half the material. If I have a partition coefficient of 0.1, we extract about 1/10. So we generate some selectivity, but remember that the selectivity is finite. So that's another one of the challenges that we have, is that we may, fully extract one material from our sample, but we may also extract, if we're doing an extraction or we're doing chromatography, we may also bring some matrix components along with it. I see another comment here. It says saving time is an important benefit of high resolution at low elution times, but saving solvent is important as it costs money, at least in HPLC, and I agree also with that comment as well. That's one of our challenges. That's why I commented earlier that that we do have budgets and other issues involved with our method development. You bet. I'm not going to argue with that a lot at all. That's a great comment. So I'm going to jump through a couple of slides here on extraction very quickly because we're heading into our first question and answer session. Just wanted to make a few comments about a technique that we've used a lot in my lab called solid phase micro extraction, SPME. This is the one with the fibers. We dip those into the sample, and you can do what's effectively a liquid-liquid extraction into the fiber. This is where some selectivity questions show up. Here's a comparison just of 3 of the different commercially available extraction media. You can think of them as different solvents. One of them is polydimethylsiloxane, one of them is polyacrylate, and another one is carboxyn. So those are really just 3 different extraction media. You can see that we extract a different amount of each of these simple compounds into each of these at under the same conditions. So you might think about, if I really were interested in chlorobenzene, I'm probably going to use the PDMS fiber, which shows up on the slide there as the blue stripe. And in fact, but you can also see that it will extract some other materials. So it certainly is something to think about in generating selectivity. Our sample prep will impact the chromatography. I'm going to jump over a couple of these, come to one last example, and this is also a selectivity example from Headspace extraction. Now, Headspace extraction is really simple. Just take your analyte, put it in the vial, and collect the vapor above that. In this case, these are solutions in water, and you can see that at the same, a much bigger effect with ethanol, which is strongly attracted to the water, than with the hydrocarbons down at the bottom as we change the temperature. So there are all kinds of ways that we can control the selectivity in method development. So I'm going to come to a few conclusions from this first part, and then we're open to have some more questions. Probably the main ones are to think about your analytes and your matrix. Get in there, search the literature, search online, get into discussions on that, discuss it with your customers, what their goals are. Think about your own equipment, think about what's available. I think if you're in the HPLC world and you have HPLC available, which a couple of the folks have mentioned through the online questions, I think that that's a real exciting opportunity in HPLC to get some of the best of all of the worlds. Finally, we want to think about your sort of the basics of method development. Think about your fundamental chromatography. We'll take a few minutes now for some questions, and then we'll come back and talk about some optimizing. So I think I'm probably running a bit over time, but Jeff, I think you can handle that. Thank you.
Oh, we can certainly handle that. That's great information, Nick. So why don't we start off the question period. I just wanted to review everybody's responses from the first poll question. The poll question was, if you don't recall, in your current position, which method development approach do you most commonly use? The split came down like this. 22% of you develop methods from scratch. 25% adjust and optimize internal methods, 21% adjust and optimize external methods, and 3% of you use validated methods without any optimization. And then the remaining 28% of those respondents do not currently develop methods in their position. So an interesting split, pretty equally distributed across most of the answers except for the non-optimization option. Yep. Yes, it goes to show how important optimization is.
Yep. Well, I think that's one of the, thanks Jeff, that is a very interesting result, and I think it does present one of our challenges, I think one of our big challenges, both in method development and a little bit in teaching it, is that it is a little bit of a different approach if you're starting from scratch versus if you're optimizing a method or taking an external method and working with that. One of the things that was interesting to me is that nobody really reported that they don't do any method development at all. I'm going to suggest that the 28% that don't do method development right now in their jobs would like to be doing method development, and I think that's one of the, I think that's certainly one of our reasons for being here talking about this. At the same time, those approaches are a little bit different. They're also kind of similar because you're still kind of doing the same things. Even if you're optimizing somebody else's method or a method that's already been developed, you still want to go back and think about what the state of the art is. Maybe somebody else has already invented that wheel and you don't have to reinvent it. If you're developing from scratch, of course, we go straight to the, we go to the literature and see what we can find there. So the approaches aren't that much different because we still need to do our homework up front, before we get to the instrumentation. So it looks like I've got a couple of questions here from the from the system. I see here, aside from PDMS, what is your preferred GC stationary phase? And for those that don't know what that is, PDMS is polydimethylsiloxane, which you maybe have heard of it as a DB1 or an HPB1 or an SPB1 or an RTX1 or whichever of those you're familiar with, and that's 100% polydimethylsiloxane. I'm actually what is my preferred GC stationary phase? When I'm starting a method development, I like that one. I also like the 5% phenyl, which most people know as usually some code followed by a number 5. That tends to give us just a little bit more selectivity for aromatic compounds and for compounds with some polar functional groups, which will which often we often want that from the start. So that's also a very good question. So please, let's have a few more questions.
Nick, I actually had a quick question for you.
Sure.
One of your early slides looked at the comparison between GC and HPLC approaches. Mm-hmm. This is something that we've been talking about a lot in the Sci-Mind community, but mm-hmm. Are there either chemical classes or matrices that would you could analyze by either approach, GC or HPLC?
I love the question, Jeff, and that's actually one of the areas that I'm very interested in my own research as a gas chromatographer, always looking for ways to really extend the utility of GC, I think there are a lot of compounds. I do a lot of work, for instance, in drug analysis and drug of abuse analysis. So for your pharmaceutical folks out there, relatively small molecule APIs. And what I've found is that, in that industry where HPLC really is king, I did a lot of GC work with them in developing methods for the same compounds that were complementary that they might use in an investigative process or something like that when they ran into a trouble with an HPLC method. The GC method could then be used as a backup or to assist them in looking at the data and looking at those compounds in a different way. Okay.
Yeah, right.
I've got a few more comments from the literature here. I've got from the question here that says here the poll limited us to a single answer and did not address that we may use a different approach relative to the complexity of the problem. Of course, I agree with that very much. Literature methods are always outdated and can be improved by incorporation of current technology. I'm not sure that I agree that they're always outdated, but I do agree that we can always improve them by incorporating either current technology or technology that we have in our labs that, of course, is different from whomever published that method. I'm not sure I completely agree that all literature methods are outdated because we're much quicker today about publishing than we used to be. If you're addressing cost effectiveness, some degree of optimization will always be worthwhile, and you bet. And that's one of the things, and I kind of like the poll questions because probably one of the things I've never done is actually taken a literature method, run it again, and run it in my lab. I've run it, but then I've not had that be my final method. There's always something that we come up with to make it better. In fact, that's what I make my students do routinely, is they find something neat in the literature, they'll try it and repeat it, and then I'll ask them how they can make it better. And they do that. In fact, that's a great exercise. Let's see, it says here, here's a question. Generally, how do you pre-treat biosamples such as plasma or urine? That's a great question for a whole short course. I'll suggest that one thing we can do is that's one of the things I do like about the solid phase microextraction technique is that it has lent itself fairly well to the relatively straightforward extraction of small molecules such as drugs from we've done a lot of work with both plasma and urine with that, but that is a challenge. I think probably in those types of extractions, I think probably the biggest technique these days in sample prep still is solid phase extraction.
Nick, I'm going to cut in at the moment and ask that we
probably have to move on. There are great questions that are coming on, okay?
We have some great questions you can answer as you move through.
Very good, thank you. I'll move ahead. You know what happens, you get a professor talking about things. Okay, let's move on to some optimization. I just wanted to share with you one example. Again, really, it's mostly from my gas chromatography background, but probably brings in some of the some of the ideas that we've been talking about in the beginning. And I'm going to kind of focus on one major problem, which is a big one, which is the analysis of solvents residual solvents in pharmaceuticals, because that's, again, it's a standard method. You can get this out of there. There's a general chapter in the United States Pharmacopoeia, so there's compendial methods for this. There's a huge literature on it. There's lots of traditional work that's been done on it, and there are lots of new ways that one can think about doing this. Plus there's lots of readily available information in the literature. So I'm going to just share a few examples in the next few minutes with a little bit of traditional Headspace, a little bit of FastGC, some multidimensional separations, again just thinking about how we might take a simple problem and optimize it. And then again, because the Sci-Mind folks were talking about it, I've got a few comments on the back end of this about data analysis and calibration. So here's a typical chromatogram. This is what you might see in an organic volatile impurity analysis. This is a Headspace GC example, and you can see about 10 different solvents that they separate out in about 15 minutes. And this is the kind of thing you'd probably see as the result of one of those compendial methods. 10 compounds, again, kind of a nice separation. You can see a couple of critical pairs of peaks that are very close to each other. Again, not a bad method. Well, how can we, again, what are some of the results actually of optimizing something like this? Let's say we want to optimize this, something like this for speed. Well, here's an example of a separation that was optimized for speed. If you look closely, and this is on an older instrument called an Easy Flash that was one approach to doing fast gas chromatography from a few years ago, where they actually took the column and wrapped it in a metal tube and then heated the metal tube. And here we can see 6 compounds that are separated in the space of about 9 seconds. And this was actually inside a traditional gas chromatograph with this special column device in there. But anyway, that's sort of optimized for speed. Not as easy to run. Okay, I can't inject with Headspace, or really there's no point in doing Headspace analysis because the Headspace extraction is so slow that a 9-second separation doesn't buy you any benefit. So I have to inject differently. In fact, I have to do a very fast injection to make this work. So that's a little different, kind of takes away from my ease of use, takes away from my sample capacity. I have to do a fast split injection instead of doing a nice, slow, steady Headspace injection. And I can optimize for speed. So here's one optimized for speed. The other thing you see is that the resolution's not that great. I've got 6 or 7 compounds here, not all 60 or so that you would see in a complete pharmaceutical residual solvents analysis. Here's a similar problem also with FastGC with one group of solvents. There are a few more of them here, also optimized for speed. Here's a separation in the space of about 2 or 3 minutes of now 28 different solvents. Again, not particularly difficult to do, but a little bit more difficult to do than my traditional gas chromatography. I'm still going to be injecting a liquid sample. You can see a great big solvent peak there at the end, which is not probably the best thing to do for solvents analysis. And I've still got a few peaks that are overlapped in this. So again, with going for speed, I'm sacrificing some resolution. I'm sacrificing some ease of use. Let's take a look at a few more chromatograms. Here's just another group of additional solvents. If I wanted to separate all of the pharmaceutical solvents that are in the compendium, here's another group of those solvents. You can see by this same method they're not separated well at all. So I can go just for speed, but in this case we've kind of sacrificed quite a lot of resolution to do that. Let's look at one more example, and this is a GC times GC, and you may have heard of multidimensional gas chromatography. I think we've got some folks that are involved in this out in our audience today, and this was one of the very first chromatograms generated in my lab, and much thanks to those folks for helping us get started with this. So here's how we get some more resolution. This is a first chromatogram, and you can see here that this is actually now what we're doing. If you're not familiar with this, we're actually looking down on a 2-dimensional chromatogram. So the bright spots you see there are your peaks. You can see retention time on the bottom, and then another retention time on the top, because what we're going to do is take one column, shoot our samples down the one column, which is a traditional column, then we're going to rapidly inject them onto a second column in tandem. And what that does, and if we do some data analysis on that, that actually gives us this 2-dimensional chromatogram that actually allows us to bring 2 sets of chemistries to bear to get the selectivity. You could see from the fast examples we did before, we couldn't get the selectivity. We couldn't get what we needed in order to generate the full resolution. Now this one's a bit slower. This is about a 15-minute separation, and then we can see some separation of the peaks. But even with this multidimensional one yet, we haven't quite separated everything. You can see some of those big spots there are overlapping. Let's look at the next one, which was actually our final chromatogram in this method development, where we used a combination of a nonpolar column, a 5% phenyl column, and a polar column, a carbowax column. And you can see now all 60 or so compounds are actually quite well separated from each other. You can see all the spots, all those peaks are spread out across the chromatogram. What is this an example of? Well, you can imagine it's a bit more of a complicated instrument. It's a bit more of a bit more of a pricey instrument too. So this is on the triangle. We went for high resolution, so we're a little bit further away from speed. It's pretty easy to use, but we're a little further away from speed there. So this was one where we've now optimized for resolution, but we can't go as fast. Now I'm looking at 15 minutes instead of 2 minutes. Okay, so that's again one of the trade-offs that we make. We're probably toward high resolution. We're a little bit further away from easy to use. So high resolution and moderately fast, we're not quite as easy to use because the instrumentation is a little bit more complex. But we are able to separate everything with high resolution. That's a little bit of an example of separating solvents and some different approaches to it that sort of land on different parts of that triangle. Here's just a quick sort of blow up. You can see some of the selectivity that you get on this. Just real quick, one of the the selectivity standard in the USP method for solvents really is looking for the separation of acetonitrile and dichloromethane, and you can see those two separated quite nicely here on the one chromatogram that's a blow up. You can see them also nicely separated from the solvent peak. Here's just one more selectivity example, a blow up of one of these, and you can actually see there's 4 peaks there all lined up. Those 4 peaks would have been perfectly overlapped or almost perfectly overlapped in just a traditional separation. But to get the selectivity and to get the resolution, we've stepped up the complexity of the instrument by moving to this 2-dimensional separation. And that's one of the challenges that we have. If we're going to buy the higher resolution, we're either going to go slower or we're going to go more complicated. And those are some of the challenges that we have. Here's just one more example, and again this kind of brings in the idea of equilibrium constants. In pharmaceutical solvents, the standard compendial method from the USP, from the United States Pharmacopoeia, addresses almost all of the solvents. But it doesn't address these 6. And so I term them the difficult 6 because they're just not, the method kind of leaves you hanging, and if you want to run these solvents, you have to come up with your own method. Well, this is an example actually of what we were able to do is take advantage of chemical equilibrium and take advantage of the SPME technique in order to extract these solvents and to run them, because the big problem with these is that they're all high boilers. So they interfere with traditional solvents that are used in the traditional methods for this. Our approach was to use SPME, and it was actually quite simple that we just took one of these SPME fibers and stuck it down into a vial containing these solvents and heated it up. And by doing that, we were actually able to extract these difficult 6 solvents, taking advantage of the fact that I don't need to heat them all the way to their boiling point to get some of it into the vapor phase, to land in this SPME fiber, and then we can take the fiber and inject it onto our gas chromatograph. So again, a fairly straightforward application, but still the kind of thing where we're bringing these concepts of the basic chemistry of the compound into our method development example. In this case, this was very traditional instrumentation, an older 5890, 5972 GCMS, an old carbowax-based column, and a commercially available SPME device was able to solve that problem. So just one sort of quick example of some of some of the method development ideas applied to some different chromatograms. Again, I hope you could see some where you might fall in different places on that triangle. The higher resolution was a little further away from speed, a little further away from ease of use. Fast and easy was further away from high resolution, and that's a trade-off that we're always going to be thinking about. I'd like to close for a few minutes today, and then we'll move on to some more questions and discussion, because I always think that's where the good part of a seminar happens anyway, is to think about some quantitative analysis. Because at the end of your method, you've got your data, or we're getting our data, we still have to take that data and turn it into information and turn it into something useful. And of course, in GC and in HPLC, we've had lots of quantitative analysis methods and lots of calibration methods. I wanted to just share a few quick comments about that, because I think with the instrumentation that we have today Again, I'm grateful to the folks that brought up HPLC, because that instrumentation, with the good instrumentation we have today, I think that's also causing us to rethink a little bit about how we do our calibration and our quantitative analysis. Seeing a lot less need for things like internal standards today. We can actually get, the way the spectroscopists can, back to traditional calibration curves. Just to remind ourselves, an external standard calibration is just like the calibration curve you did when you first learned UV spec back in school. You ran your standards at different concentrations, you measured the response, you plotted a calibration curve, and out came quantitative data. The challenge we have with this is that it requires very, very good, accurate, precise injection. Now at HPLC, that's no problem. Your automatic sample loops are terrific at injecting. In GC, we're injecting the same way we still did 50 years ago. So it's not quite as easy to get that precise injecting. Auto samplers are doing better, but they're just doing a faster version of what we did 50 years ago. So it's not quite as easy in GC to use traditional external standard, but we're getting a lot better. So actually, when I develop a method, we've heard of internal standard methods, I actually develop both at the same time. I'll do the internal standard and the external standard and run both sets of data at the same time, and then decide for myself whether I need to keep the internal standard. So what do I mean by that? Well, we've all probably done this before as chromatographers, or we do this in methods that we're running. We just add this contaminant to the sample. You add this extra compound in there that we carry through our sample preparation and our injection. And of course, what we then do is we measure instead of just the raw peak areas, we measure the area ratio of our analyte of interest, of our standards, with that internal standards, and plot the area ratio to the weight ratio. When we do that, that kind of helps to normalize out some of the variation in extraction and injection techniques. The challenge with that is that it normalizes out some of the variation in extraction and injection techniques and can actually hide a problem with extraction or injection. So what I tend to like to do is do both calibration methods. I look at both, because both calibration curves, the external standard and the internal standard, should give you the same result. If they don't, then we know we've got something going on with the injection or with the extraction that we need to go back and look at. But that certainly is also one of the considerations when we're developing a method. So when I'm doing this during method development, I'll go ahead and set up for the internal standard. Because it's more complex, it adds this contaminant. It actually means I have to overdevelop my chromatography a little bit. And then I'll do my calculation when I'm validating the method. I'll come back and decide for myself whether I need to keep that or not. What I'm finding very often today is that we don't need to keep it. That the instrumentation has finally caught up with our ability and our thoughts on calibration, that it's just so much better and the automation is better that I'm finding less and less need for this. Finally, we may, of course, if we have dirty samples, use standard addition methods. I've done quite a bit of this kind of quantitation, especially if I have really dirty samples like the urine samples or nasty biological matrices or things like that. Standard addition methods can be very, very helpful in that context. So we had a few quick comments about some things, but I want to go ahead and close up now, and then we'll have plenty of time for some discussion. Where to start in method development? Gather your literature, get information, get as much as you can about your samples, about your customer, who is going to be running this method. Meet with the people you're going to be running the method for. Actually, one of the things I like to do, I work here at the university. If I'm doing method development for somebody, I like to go out and visit them at their place. I want to see their instrumentation. I want to see their plant floor. I want to see where their samples are coming from. All of that is going to help me be a good intelligent chemist and chromatographer excuse me, when I have to go into the lab and develop the method. For instance, if I know that they have 10 GCs in the lab and 1 HPLC, that means I'd really like to try to perhaps develop a GC method for them. Or if I see that they're predominantly HPLC experts, that's also going to help me think about how to take care of them as a good consultant. Then we're going to choose things. Is it GC or is it HPLC, or is this thing not amenable, or do we not even need to use chromatography to solve the problem? That's something that actually also comes up more and more as we get better sampling into techniques like mass spectrometry and some of the other spectroscopic techniques. We might not even need to bring chromatography to bear on this sample. Think about sampling and sample prep techniques. Once I pick GC or HPLC, then we can dive into how we're going to prepare the samples. I always keep that triangle in mind, though. And what I've learned about my customer. Who's going to be running this sample? Do I need to develop an easy method, or can they handle something more complex? Finally, and we didn't do a lot of examples of this, but I like to do then, we start off our method development really doing scouting runs. That's one of the places where that literature work helps me. If I've got a similar column, I can go ahead and set up similar conditions and give it a try and see what happens. The other thing we can do, if nothing else, if I don't have that literature, if nothing else, start with what we chromatographers call a strong mobile phase. In GC, prep up a sample and inject it with the column nice and hot. In fact, I'll suggest an isothermal run at something near the maximum of the column just to see if peaks come out. Or a very fast temperature program, from the lower end of the range to the upper end of the range, just to see if you get peaks out, and then you can go from there. In HPLC, just run a short column and a strong mobile phase. Again, just to see that you can get the stuff through a column and detect it. Because once you can do that, we can then get into all of the detailed method development operations from there. Finally, do beware of the back end. Do beware of what kind of data analysis requirements do we have, what kind of calibration are we going to wind up doing, what are our requirements for detection limits and those sorts of things. That, of course, is going to hit us on the back end. Once we know we can separate the compounds, how do we take that separation and then translate it into whatever it is our customer can really use? And with those comments, I think I'm going to go ahead and thank you all for participating. Please do consider being in touch with ACS and with Jeff Standish if you're not in the Sci-Mind group, for most of you out there, and take a look at that. It's an opportunity to have interactions like we're having today on a very regular basis with a whole group of outstanding subject matter experts that ACS has brought together. So with that said, I'm going to thank everybody for being with us this afternoon and open the floor up for some more questions or comments, please. Thank you.
Thank you, Nick. That was wonderful. Before we get into answering a few of the questions that have been submitted, I wanted to launch our second poll question and give you all about 30 seconds to register your answers. And I'll be closing it up in 3, 2, 1. All right. Nick, I'll let you go through some of the questions that have piled up and spend a couple minutes answering them.
Sure. Okay, actually, I love this one. It says here, excuse me, how do you use partition coefficients, either octanol water or log P, to select your column of your sample prep? I love the question, because that's I think they those, especially if there is that data available to you, either from your own development folks or in the literature. I think it's very useful. Of course, an octanol water partition coefficient is which I'll use as one example, is a pretty nice measure of polarity. So a very high octanol water partition coefficient is going to tell me that this thing really does like our more fatty matrix of something like a nonpolar column. Actually, that tells me that that's going to probably be retained fairly strongly on a nonpolar column. So what I might think about looking at, though, is if I have my analyte, which has one partition coefficient, and then either other impurities or other compounds in the matrix that I want to separate it from that have another partition coefficient, think about how different those are from each other. And if they're very different from each other, that tells me I'm probably going to have a relatively simple time separating them. If they're very similar to each other, then I've probably got a tougher separation problem. But it's a good place to start, at least to kind of give me a feel for what's going on there, again, before I inject them. Are these going to be strongly retained on a nonpolar column? If they are, that may also spur me, if I want to retain or elute them quickly, to move to a more polar column. But it helps with it for a good place to start. Here's another question. It says here, I've got 3 kinds of samples in a mixture. How can I identify a peak of each sample? That's again a really can be a really challenging problem. I'm going to sort of assume that we're talking about I've got a really complex mixture, and I've got perhaps multiple phases present or something like that. That's one of the things where I'm probably, again, going to probably look at the sample preparation as much as the chromatography to help me with that selectivity. Because I certainly want to inject, we don't inject pure materials on our chromatographic systems, but we do inject clean materials usually. So I'm going to think about if I can remove some of that bulk matrix component that's probably interfering with some of the analytes and get that out of the way before I do my chromatography. I'm going to think about that. I like the question. How would you start developing a method for a new product where no study is made before? Again, that's a great question. What I'm going to do is I'm going to go right and I'm going to ask a lot of questions of whoever it is brought me that stuff to work on in the first place. So I'm going to go to the synthetic chemists at my company and I'm going to ask them all those questions that we talked about up front. I'm going to ask that of the development chemists at my company. And I'm going to try to get as much of that information from them as I can, because that's going to help me to develop a better method for them. But of course, much of that information, maybe not all of it, should be available if the synthetic chemists are doing their job and doing the characterization that led them to believe that they actually have created the compound of the structure that they're complaining, or that they're claiming that they have made. A comment: delays in publication are much shorter, as you indicate, but are less likely to impact regulatory methods and compendial methods where the cost to the end user are greatest. Agreed. I think that's also one of the challenges with regulatory and compendial methods. And very often, again, I think about those regulatory and compendial methods, at least as an academic I can do this, as the place to start. And you'll get a lot of good ideas, a lot of background method information from that. But today I would not go to the USP and take a method right out of the USP, for instance, and just use that method blindly. Not today, because it probably is using a column that was developed 20 years ago, and the columns today are much better. But I would certainly use that method in those conditions as a starting point for my own development and validation. I think that is actually still a very good thing to use. Let's see, what program have you used to draw a previous histogram? I can tell you that probably all of the charts here, if I drew a histogram, that was just drawn in Excel. But that's also, again, one of the data analysis challenges that we do have. Let's see, having experienced the unpredictability of catecholamine, EPA, NE, and DA extraction from biological samples, urine, and blood, I think internal standards have to be strongly considered in such cases. You bet. I work a lot with urine and blood samples, and I agree 100% internal standards are a great way to go, because you're almost always going to be doing a complex extraction scheme prior to your chromatography. And the internal standard will help you to account for some of that variation. I still like to do the external calculation, though, because that helps me to understand how much variability I am getting from that extraction method.
Nick, why don't we take one more question, maybe the one from
sure.
Corey, and then we'll wrap up.
Okay. I love it. How does the flow rate of the mobile phase typically affect resolution in GC or LC methods? Boy, I love the question, because that's you've really hit on a fundamental piece of the theory, and just the quick version is, at most practical flow rates, you'll find, and there's a great theory about this. If you go to a book on basic gas or liquid chromatography, just go to the index and look up the Van Diepter equation in that book on the basics, and that'll tell you some of the detail. But at most practical flow rates, you will trade a little bit of resolution for speed, in that the higher flow rate will cost you some resolution. But at the same time, depending on the conditions you're using, excuse me, the higher flow rate, the trade-off will be to your benefit to go to the higher flow rate. The big detail on that, and that's actually a great thing to be involved in the Sci-Mind group, because we do a little bit more theoretical detail. But definitely check the chapter on theory in one of the good books. In fact, if you're looking at gas chromatography, check the theory chapter in Bob Grobe's book, Modern Practice of Gas Chromatography, or Professor McNair's book on Basic Gas Chromatography, and that'll kind of walk you through some of the detail on that. But again, at most practical flow rates, you're really looking still at trading off some resolution for that improvement in speed. So thank you all very much for the great questions and the discussion today. I'm told by the organizers it's time to quit at this point. So thank you everybody again very much.
Nick, thanks a lot for fielding those questions, and thanks all to the viewers for submitting them. Before everybody signs off, for those that are still online, we have one final poll question that, if you have 30 seconds to stay and answer for us, would be very helpful going forward. So it should be showing for you now. And we appreciate your responses. So let me again thank Nick Snow for a wonderful presentation on method development. I want to mention to those of you that were in our group of early registrants that we will be transferring you over to our Sci-Mind discussion here in a couple minutes. The public webinar is now concluding, and we hope to see you on our Sci-Mind website. You see the web address listed there, and check out our features campaign, which gives you an example of a number of the types of live sessions and content that's available for the training within Sci-Mind. So again, thank you everybody for viewing, and for those that are going to stick around for the discussion forum, hang tight. We're going to take a couple-minute break. We'll start up the discussion in about 3 minutes. So grab a drink of water or hit the restroom and come on back. All right, so thanks for your patience, everyone. For those of you that were not early on in the registration, you are going to be dismissed if you are still online. If you have any questions or want further information, please feel free to contact myself or the Sci-Mind team at a later date. So I'm going to go through and unmute everybody that is in our discussion session right now. If you care to mute yourself, feel free to, but I want to give you the opportunity to interact with the group. And if we're getting feedback from certain people, I will mute you. Feel free to give me a chat message if you wish to be unmuted or can't figure out how to do it yourself. So I want to, again, thank Nick for a wonderful presentation. The point of this discussion session is kind of twofold. On one end of things, we want to give the viewers of the public webinar session that are not members of the Sci-Mind community a chance to ask additional questions and learn a bit more about method development approaches. But for our Sci-Mind community, we also want to take this opportunity to have some of our SMEs, namely Mike Hicks, is going to lead us in a little bit of discussion with some questions that he has, and see if we can solve some problems that people might be having regarding method development approaches. So hopefully you should all be able to see on your screen a list of questions that Mike's put together for us. Everybody see that?
Got it, Jeff.
All righty. So, Mike, I'll turn it over to you and to Nick and the rest of the subject matter experts to get us going with maybe a couple examples from your own method development approaches or case studies or problems that you've seen, and likewise for any of the Sci-Mind learners and viewers from the public audience, if you have additional questions for Nick or questions in general about method development, feel free to speak up or feel free to use the chat window or question window again, either way.
Hey, Jeff, just as a heads up, I'm going to have to duck out shortly, just as a heads up.
All righty, so maybe we'll start with any additional questions for Nick. Are there any additional questions out there from the webinar or aspects of method development that you want to learn a little bit more about? No questions? Subject matter experts, anybody got any questions out there? We had a great one submitted during the presentation from Anka. Anybody have any comments or questions? Tough crowd out there today.
Yeah, quiet out there.
So, Mike, why don't you want to maybe go through some of your questions here on the list, and we can see if we can generate a little bit of discussion. Mike, can you hear me? You're muted. You have to unmute yourself, Mike. There you go.
Can you hear me now?
Yep.
We can hear you now, Mike.
Yeah, so essentially Nick hit on some really good points about what method development approach to use. It's not something that you could just plan or say, well, I think I'm going to go with this approach. It's problem-driven. It's very problem-driven, and it's very much, it depends on what kind of a thinker you are analytically, but essentially going to the chemist, those are all really good points about getting as much information as possible. But what's going to end up happening is your ultimate limit is going to be essentially what options are available to you. So in terms of what you have in the laboratory, what's available, what instrumentation is available, is critical, because you can't. There's some things that you can do with GC. Nick emphasized a lot of GC work. There's some things, for example, really high boiling point solvents, not solvents, but analytes that you simply to do by GC would be a very difficult option. So you really have to rely on LC techniques. So I just would like to try to take a survey, maybe if there's one particular problem from someone they want to they have questions about and would like to know about approaches. I could maybe share some of my experiences with it, and all these things were really touched on in the cohort, was about the what type of properties do you know about the analytes that you're using. You really want to, is it one of these situations where you know a lot about the analyte that you're using? It's a method of development for a particular compound. Or is it something where you absolutely have no idea what's in your particular sample? For example, people doing natural products isolations. So, and then maybe some of the details of your matrix. So if someone, I guess, would I be able to see their questions from here, Jeff?
We can relay the questions to you as they're submitted.
I have a question, Mike.
I have the speaker all the way down. Sorry. Could you repeat that?
I said I have a question, Mike.
Oh, sure. Great.
Do you have any recommendations regarding a 2-hour separation time that we have for a gigantic mixture of peptides? We do a lot of proteomics in our lab, and we have giant mixtures of peptides that we don't know what all the peptides are in there. And right now our separation time for that is 2 hours, and I was wondering if you had any suggestions on how we might be able to cut that down.
So two hours.
Yes.
Yeah, do you have access to UPLC?
Unfortunately not.
What are your current conditions right now? This is Bill.
We have a very slow gradient. Off the top of my head, I don't know exactly. We're using a C18 column that's pretty doggone long, and acetonitrile and water spiked with a little bit of formic acid because the detector is a mass spec.
Okay, so are you running at, I think what Mike was alluding to is, if you're running with 5 micron particles, start moving down to lower and smaller particles. Then
Okay.
as you do that, start increasing the temperature of the mobile phase. Put the column in a column oven and start ramping that up. And what you'll get is an offset of the increase in pressure from the smaller particles, and then an increase in or sort of decrease in viscosity, and that'll kind of keep your system within the parameters since you don't have a UPLC system. And then by doing such, you'll also speed up the elution. Most things tend to elute a little bit faster at the higher temperature, and so that should shorten the rundown somewhat.
Okay, we already have our column at 40. For something potentially temperature sensitive like peptides, what would be too hot?
You tell me. I run
okay.
columns.
I'll have to do more research than that then.
So I run columns at 60 right now, and there's even a system we use with UPLC that we run at 100 degrees.
Oh, wow. Okay.
Yeah, the UPLC, though, is at higher pressure, so usually the heat transfer is faster. It can handle that. But, yeah, if you're on a conventional LC, you know, maybe up to 50 or 60 might be pushing it. But, you know, the problem is how you're having one of these tremendously long columns. I mean, historically, before a lot of the advancements in columns have come up with, as you mentioned, with particle size, people got the impression that, oh, you just, you know, you increase your column length and that's going to really help. But if you consider the Van Diemter, it's only really a square root. That you only speed it up by the square root of 2, essentially. By doubling the length, it's not going to really buy you much. So there's a lot more, like maybe looking into things that you have like core shell technologies that allow you to use conventional HPLCs without the high pressure. You know, then you can go into looking at the you know, protein columns. I had a lot of luck with, well, didn't do a lot of protein work, but with peptides, you know, there's proteo columns, there's other columns out there that affords to, if you get a little bit smaller of a particle size, you'll have a much better efficiency. And then again, as Bill mentioned, to go to higher temperatures.
Okay, thank you.
And you can reduce your column length that way.
Oh yeah, that's true too.
So I guess part of this is talking about the GC. Is there a lot of, I guess there's a lot of people doing GC in terms of, you know, how you start that development work. You'd want to look at boiling point ranges of your analytes, volatility. This precludes or doesn't include the you know, petroleum analyses and things of that nature where you may not know in some cases boiling points, but you know, it like I said, just gathering as much information as possible. I tend to do a combination of you know, where to start is to look at the literature. Look at, for example, maybe you're in a lab that only has one GC column or one LC column, and you can't afford another column. So maybe the common thing to do is find out the vendor, go to the website, see what sort of things are done on that, what kind of conditions are run on those columns. That might be a really good place to start. Like I said, you could peruse the literature, but if you do it from the point of view of your analyte and you don't have the options that are available, like buying different columns, trying different mobile phases, stationary phases rather, you know, you'll be limited. Are there any other questions out there?
Any other comments or questions from the community? I know some of you were muted because of feedback, but I've unmuted pretty much everybody at this point, so feel free to speak up if you have a comment.
Well, in the discussions, there were a couple of discussions, I guess you would say, that they were talking about subambient cooling, where they were going minus 50. For example, I think one of the suggestions was, in my work when I was doing volatiles analysis, we started out at everything about minus 25, so we could get those low molecular weight halocarbons like dichloromethane, which up until we started using those were just kind of written off as non-doable.
Okay, so with regard to the very, very low temperature, very low boiling temperature.
They acted as a kind of a cold figure trap at the front of your column, so you trapped all those like dichloromethane or chloromethane at the head of your column and produced nice needle sharp peaks, and then you do a quick heat up of your column to like 30 degrees or something like that, and then you do your normal 5 degrees or per minute on up to your the end of your run or whatever. Works great.
Well, that's good to know. I wonder if Nick Snow is still online, because I'd be curious to know if any of these things would work with the SPEMI technology that he had mentioned. I always had problems with, and I'm not as familiar with using a cold finger, but the problem is if you're running, if you have to do a large, like a series of analytes that go from really low temperature to really high temperature, the difficulty in the length of your run is now it has to go back and re-equilibrate or come back down to that. But if you're using a cold finger trap and then introducing it into the inlet, that might be
no, it's not. It's not really a cold. It's cold finger type. You're actually using your subambient cooling in your oven with liquid nitrogen.
Okay.
So
what do you? So I guess from your point of view, what's your question in terms of development?
I was just pointing out that it, as a method development, or whatever, it allows you to get all those low boiling point compounds, and as a side product, it also makes needle sharp peaks for the rest of your peaks.
That's great. Yeah, that's good to know. You'd have to show me sometime.
Answering your question about SPME. Hello?
Yes, yes.
You are asking if this would work with SPME, having a cold trap? Yes, it's done.
It is done. Okay. Would it make it more efficient? Because I can imagine having, I guess if you're completely on the end of these high boilers, that would be a real, low boilers, that would be a real problem if you had a larger range of it. Is it something that SPME could actually simplify?
Well, I'm not sure about the large range because this is usually used for VOCs, but it is used especially if you want to capture low amounts of even benzene, for example. If you're doing a trace analysis, they use a cold trap to capture benzene, for example.
Okay.
So it does help with for higher sensitivity, for example, even for benzene.
Okay, that's great. That's good to know. There's been a question online about, I'm interested in knowing everything about GC and HPLC theories and videos and what kind of applications that we can use on undergraduate student laboratories, for undergraduate student laboratories. So, I guess, does anyone have any suggestions out there before I put in my 2 cents from the panelists?
Is that question from Emma, by chance? Or
yes.
Iman? Sorry.
Iman Sham, right?
Yeah. I've responded to Iman also through the chat window, but I'd be interested to hear your thoughts as well, Mike.
Well, I have to say that it would be good to start with Sci-Mind, but it's definitely a very good resource to be able to actually talk with the professionals in the field, and many years of experience in the panelists. There's other things when you just basically, like Nick had mentioned, Google Scholar. There's so many resources online that, if you want to, depends on if you're looking for something in particular, like instrumental. If you're looking for theory, there's plenty of things out there on theory. HPLC theory, obviously the first resource would be Sci-Mind. There's tons of training and literature on these cohorts. In the whole thing, I was looking through some of the past events. There's videos, and it really, really explains things very, very well. And there's other places you could go if you buy, for example, introductory UPLC book where they're trying to explain the Van Dienster equation and things like that. It goes over the theory very nicely and covers it.
Yeah, they might go to some of the instrument manufacturers as well. They might have some videos, etc., that they could use.
Yeah, absolutely.
Also, I don't know if Paul Roswell's on the line, but boy, he's got like a website that's really useful where you can kind of play around with a variety of different separations. He has it for LC and GC. Really nice to play around with. And I know that Jeff has that information already included in Sci-Mind.
Yep, and it's a great segue, Bill. In fact, the cohort learners that are on here are certainly well aware that they're going to be working with the simulator you're referring to, Paul Boswell's HPLC simulator, just next week. We'll be having a demo from him, and then there's assignment. But certainly happy to share information with Iman and others that might be interested in accessing that and becoming part of Sci-Mind. So thanks for all those comments. Are there other questions? We have probably about five or so minutes, 5-10 minutes, if there are more questions. Or Mike, if you want to move down your list and maybe pose a couple of the questions at the bottom, that'd be great too.
Right. So I guess while you're thinking of questions to post, I guess we can just, you know, the important thing is that sometimes you run into a situation with LC, for example, where you might be just, you know, you're trying to dissolve your sample, and it's just not a water-soluble sample. And everything you've done in your experience tells you that, oh, reverse phase is the way to go. And you know, currently there's a number of options for you. I mean, historically, you'd go to a normal phase separation where you could use like a hexane or an IPA, but I think what's becoming increasingly popular now that it just hasn't caught on yet is SFC. So with SFC, it allows you to have liquid-like permeability, gas-like diffusivity properties. You can essentially really gain a lot of efficiencies and run these at really high flow rates to get high efficiency at the same time. So you know, these are things you could do in the normal phase mode. So if you're running an intermediate, for example, and it's only soluble in DMSO or DMF or THF, and you can't really, well, THF is kind of is really a more polar solvent, but you know, if you have a non-polar solvent, you can essentially look into other modes. The other thing is to look at your parameters. You know, what's available for you to change? What are the variables in your GC? You know, you're going to look at, someone mentioned a cold finger and essentially using a temperature gradient, what columns you have available to you, what thicknesses, lengths. You know, what are other options? Split mode, what kind of injector are you using? Splitless. You could also, with LC, look at your different parameters to change. Do you have, you know, for your injector, what's your injection range? For example, what kind of column length, particle size we mentioned, how, you know, mobile phase changes. All of these things change selectivity, as Nick had mentioned, in order to get maybe better. Change your pH in reverse phase, yep, absolutely. And then essentially, if it's a sample prep for a given method, in a lot of cases, you know, a lot of us think in terms of maybe what would be needed up front. A lot of times it makes it a hell of a lot easier from the analytical point of view is if you do your work up front in cleaning up the sample, especially if you're trying to do quantitative work. You know, we talked about internal standards, and also Nick mentioned standards addition. All of these things, they will help, but you have to really make sure that you have a good selectivity in your method. And I guess I don't just mean that you have resolution of an analyte. You could have a mass spec selectivity where you're using a single ion monitoring mode, for example, or you know, maybe an electrochemistry, an ECD detector. But there has to be some way that you could basically distinguish your analyte completely from the matrix, and do it if you need to do it quantitatively, this presents other challenges such as matrix effects. These will all come back to haunt you if you know, if you don't clean your sample up front first.
Yeah,
is there any other specific problems or?
Yeah, I wanted to ask if any of the our Sci-Mind learners have any specific questions. There's been a lot of posts on the discussion forum over the past few days, and if you have any questions that may have come up in hearing some of this information from Nick and Mike today, feel free to ask a question while we have about 4 minutes left.
I guess if you can't think of it now, too, we periodically check the discussion board for those in the cohort, so you could always post your questions, and then we'll get back to you.
Yeah, I know that I got a couple questions about contact information and learning a little bit more about Sci-Mind. So for those of you that are not in our current cohort, here's some information for you to check out, and also my contact information there, along with my colleague Lauren Lamoro. feel free to get in touch with either of us, and we can answer questions about how to sign up for Sci-Mind, how it works, what the benefits are, and certainly check out the features page, that link there at the top of the screen. That'll give you a sense of what to expect from our live sessions and whatnot. Are there any other questions out there at this point?
Well, you did answer one question, how to pronounce Lauren's last name.
She gets a lot of varying pronunciations, that's for sure.
So I have a question. It's Bill again.
Sure.
It's a bit selfish, but I'm going to ask it anyway, because there's so many GC people on here. So is there a set of, or a generalized chiral GC column out there?
There are some that are sold for that purpose.
Not utilized tremendously. I mean, is there? I need to do some. I have small amino alcohols. They seem volatile, so I was thinking maybe GC would be a better approach, and they're very small, near or less than 100 molecular weight, and it tends to be problematic even on my SFCs.
Well, you'd probably want to look more towards the analyte first than towards the chiral end of it.
Well, I mean, I tend to, you know, I can always add like a CBZ or something to it, and that helps. But then I got to take it off again.
Right.
Is there any way to do it on the small molecule? You know, there's just a general approach for GC. You know, you grab such and such a column, you run it, or is that it does not really occur in the GC world?
Like I said, there are some that are sold for chiral purposes. I could just hit the column manufacturers up for it, I guess, and see if it would meet your purposes or not.
I've used chiral GC. I'm not really a GC person, but used chiral columns for GC, but not for something that volatile. So I'm sort of, you know, for an alcohol or something like that, that's, you know, I would tend to go, if I had to do it, I would try to do SFC first with a chiral column. Only because SFC, you're putting it under pressure. It's supercritical fluid, so you could easily see it, and you have a lot more choices, I guess, in terms of chiral rate to be able to resolve it. There's a number of chiral columns that work with SFC very well. If you have SFC as an option.
I do, and I've been through it. I've actually, you know, I probably have 30 or 40 phases here, and I've tried them all, and it's kind of it's a sticky problem. We could take it offline if anyone's really interested.
Yeah, I mean, that's a great question to post to the discussion forum, Bill, if you want to take a minute and put that in there later today.
I might.
We can get a discussion going that way. Any other comments or questions? All right. Well, I want to thank. Well, Nick's already gone, so we thank him. Mike, I appreciate your effort in putting that list of questions together. It really generated some good questions, and I appreciate everybody sticking around for this discussion session. Let me take this opportunity while I have the majority of the learners here online. You may have seen an email I sent out to all of you earlier regarding the Lab 2 and 3, Week 2 and 3 lab exercise. I did hear back from Chris Golder, and she's one of the 2 people, Kim Wilson being the other one that looks like they're going to be able to run the sample. So Kim, I wanted to touch base with you and see if you have run the sample yet on the HPLC, or if you were planning on doing it in the next few days.
Yeah, I'm planning on running tomorrow.
Oh, super. So just to fill the subject matter experts in, due to our current government shutdown, a number of our learners who are government employed don't have access to their instruments. So out of this 5 people that we sent samples to, only 2 of them are going to be able to run it. So what I proposed to them by email today and sharing with you today is that we just make this a community, a group lab exercise. So when Chris and Kim get their runs, their chromatograms, they'll post them on the discussion thread, and then all the learners and SMEs will have a chance to look at the data, provide comments within the next 5 days or so. Sound good?
When Nick had that triangle up there with the goal resolution or whatever.
Yep.
I was thinking maybe we could send that on to Congress. Maybe that would help.
Yeah, I can run it down the street here. So that's all I needed to say about the current lab assignments. So that'd be great if you guys can post them. It's no urgency. It's a 2-week lab assignment. Our next live session will be a week from today, on the 10th, and Paul Boswell will be discussing his HPLC simulator with us. So hopefully see all of you in the Sci-Mind community back for that live session. I want to thank those webinar viewers that stuck around and participated in the discussion here. Please feel free to give me a call or email me if you have further questions about Sci-Mind or about content that you saw in today's presentation. So with that, thanks again, everybody. Have a great rest of your evening, and I'll see you all a week from today.
Thank you.
Thank you.
Take care.
Bye.
Bye.